Good afternoon, everyone. I am Hande Sarantopoulos from the Communications Office. It's a great pleasure to welcome you to our fifth lecture of Leaders in Science, the Presidential Lecture Series. It's a distinguished tradition at Koç University that brings together visionary scientists and thought leaders whose work is shaping the future of research and innovation. Curated and hosted by our president, Professor Dr. Metin Sitti, this series continues to highlight pioneers at the forefront of their fields, fostering meaningful dialogue and inspiring our academic community. Today's lecture will introduce us to exciting new physics that emerges when ultra-thin materials are combined in innovative ways, opening doors to discoveries that could shape future technologies. I now invite our president to introduce our distinguished speaker.
Thank you, and hi everyone. It's my great pleasure to open our today's presidential seminar, which will be given by Professor Ataç İmamoğlu. So very briefly, I know Ataç since my times at ETH, so I knew his name a lot, but I never had the chance to meet him before. And then when I joined ETH as a site-appointed professor, we had a nice coffee chat in Zurich. And since then, we have been in touch. So very briefly, his bio is, he's from ODTÜ, METÜ Electrical Engineering, Electrical Electronics Engineering. And then he did his PhD at Stanford in Electrical Engineering, and then became an assistant professor at UC Santa Barbara. Then he joined ETH in 2002, and since then he has been there. He's a very well-known professor in quantum materials and optics, and we will hear today some of his research activities on emergent phenomena in atomically thin semiconductors. Also, I remember his name because he had 2 times ERC Advanced Grant. Is that right? So from my colleagues, so it's a great honor also to receive such a prestigious grant to ICE. We are very excited to have him, and he's also a good friend of our university. He was a distinguished scholar some time ago, and he has been collaborating with some of our faculty members. And also now, recently, almost 1.5 years ago, he joined our board of trustees as a member, and he's contributing not only scientifically, but also as a board member to our university in many different perspectives. So we are very happy that he's here today, and I'm very happy to now change from the mornings, all the administrative discussions to science, and I'm sure he's also happy about that. So let's welcome him from Zurich, and we'll look forward to hearing your talk. Thank you.
I see many physicist friends, but I try to make the talk more accessible. I never succeed in making it accessible to everyone, but I'll give it a try. But the main focus would be to tell you about, or to hopefully excite you about what one can describe as emergent phenomena in the new 2-dimensional materials, and particularly semiconductors. And then also try to show you one experiment that we have done, which at least I find exciting. These are the people in my group, or formerly in my group, that did the experimental work, and these are our collaborators. All right, so basically the topic is about quantum materials, which is rather broadly defined. And so what I would like to do is I'd like to sort of make a statement, take you back, and remind you that understanding the solid state, any solid that we encounter with, requires quantum mechanics, right? And so without quantum mechanics, we could not explain why matter is stable as is. And here the 2 important contributions, or 2 important principles, are the Heisenberg uncertainty principle and Pauli exclusion principle. But the fact that this is essential tells us that all materials require quantum, or are quantum materials in some sense, but this is not the way we typically use the definition for quantum materials. So most materials that we deal with have electrons, and these electrons behave as if they are independent particles. Okay, so we can describe the properties of the materials by coming up with the model where electrons move in an effective potential. So this could be a potential generated by the ions, but also an effective potential that is generated by the other electrons. But even though the electron, the single particle, interacts with ions as well as the other electrons, we can neglect the entanglement between them. So that's, let's say, using the terms that have become more popular with the advance in quantum information processing. So so this is a very general category, and most of the materials we deal with can be described in this framework. So metals, for example, have many free electrons. They move like a fluid. And in many cases, we can even neglect their interactions and use a so-called Jellium model where electrons are freely moving and just being subject to Pauli exclusion and Heisenberg uncertainty. And these are, as you know, very good conductors, but not perfect conductors. Then there are insulators like glass or diamond, and these have no free electrons. So all the electrons are tightly bound to their host atoms, and they're good for isolation or for other reasons. And then there are semiconductors, which are, of course, essential for the electronics industry. And here, what makes them special is that we can actually tune the properties or the electron density such that we can, by using an applied voltage, we can turn the material into an insulator, and then by changing the voltage, it can become a reasonably good conductor. And this is an essential element of how, let's say, the field effect transistors work. All right, so these materials or these properties are very useful, and we cherish them. But as physicists, we are interested in more, that we are interested in sort of a broader or a different category where the interactions are so important that we cannot treat them as an effective potential. The electrons, because of their interactions, correlate with each other, and this correlation results in entanglement, and the information about the system is stored in these correlations. So when this is the case, then we can no longer use, say, a single particle description, right? And so what makes these interesting or challenging is that they have interesting properties that are difficult to predict based on the individual atoms or individual, let's say, lattice structure that we have, but they're also rather difficult to make predictions about, to make calculations about, and you might know that one of the 4 pillars of quantum information research is quantum simulations, and the idea behind quantum simulations is to be able to make predictions about these strongly correlated materials to understand what they are about. Okay, so here I will basically give you 2 examples of quantum materials, and my physicist colleagues might disagree with me because these are, let's say, the simplest type of quantum materials that are relatively easy to explain, but there are nevertheless technologically important and well, at least the first one is, and are interesting nevertheless. So the first one is superconductors, and in superconductors, electrons form pairs, which is one of the more counterintuitive aspects, because we do know from chemistry and physics that the electrons repel each other. They have strong Coulomb repulsion, and yet in solids, under certain conditions, they like to form pairs, and when they form pairs, they undergo a process which we describe as a condensation. When that happens, they become free from any resistance. Okay, so this is the curve for a lanthanum nickelate, I guess is the name. So this is how the resistance of this material scales with as you lower the temperature. You see that the resistance is reasonably small but finite. It goes down with temperature. This is something you expect in metals. I won't go into the details, but at around 70, 80 Kelvin, you see that there's a sharp drop of the resistance, and the resistance value that it reaches is 0. Okay, so the temperature is finite, but the resistance is 0. So this is let's say the typical signature of a superconductor, and you can see that this would be, if this temperature were above the room temperature, this could be technologically very important, because that would get rid of heat generation in transfer of electricity. Okay. Now, these also have other fabulous properties, that they're perfect diamagnets, so they expel magnetic fields, and this is something you can use to basically levitate magnets above a superconductor. Okay. And then the other extreme is not when electrons effectively attract each other, but in the limit when electrons really dislike each other so much that the best way for them to minimize the repulsion that they get is to crystallize. So instead of forming a fluid, as it is the case in let's say, more traditional materials like metals and semiconductors, in this case, they actually crystallize to maximize the distance between them. Okay, so these blue spots are where electrons are in. They form a triangular crystal in a two-dimensional material, and they become insulating, a very good insulating. So this is something we actually demonstrated back in about 4 years ago using optical means, but this data is from STM and was obtained by Ali Yazdani's group in Princeton. All right, so when do we observe these strong correlations? So what is necessary is to have, as I've been emphasizing, is to have strong interactions that lead to correlations between the electronic states. So there are two energy scales that we need to deal with in solids. One is the kinetic energy associated with the motion of the electrons, and that's given by p squared over 2m, or 1 m times b squared. Okay, so in two-dimensional systems, this kinetic energy scales as the electron density. So the higher the density, the larger the average kinetic energy would be, and that's due to the Pauli exclusion principle. Now, the Coulomb interaction is, again, the form you might remember. It goes as 1 over the average distance between the particles, and that scales, therefore, as the square root of the electron density. So the ratio of these parameters, of these characteristic energy scales, is so-called RS parameter. And it depends on a number of sort of properties. So, for example, the effective mass of the electron is important. And more importantly, it scales with 1 over the square root of electron density. So we have this counterintuitive scenario that the lower the density, the stronger the interaction effects become, even though the interaction strengths themselves go down with by lowering the energy. Okay? And the reason for that is the competition with the kinetic energy. So if RS is small, if the kinetic energy is large, then what you see, this is a sketch of a semiconductor band diagram, a filled valence band, a half-filled conduction band. Okay, so you see this kinetic energy cost comes from the fact that each state for any given momentum can only occupy 2 electrons, and that's the Pauli exclusion principle. And therefore, as you put more and more electrons, as you increase the density, the momentum has to become higher and higher, and that results in this kinetic energy cost. Okay? And in this regime, if the RS is small, electrons are free to move around. They have what we call translational symmetry. The physics is the same anywhere we look at. Right? By lowering RS, we can add, or lowering the electron density and increasing RS, then one can reach this Wigner crystal state that I told you about. And for that, this ratio should actually exceed 30. Okay, so it's difficult to get to this regime. And what is maybe the most interesting is the transition between the two, where the nature of this transition is still not fully understood. And actually, new sort of computational techniques like neural networks are helping us to understand the phases that separate these two relatively easy to describe phases. Okay, in this case, the continuous translation symmetry is broken. The physics is not the same anywhere you look at. You only have discrete translation symmetry. All right, so So this is the case when you need to have very small, large RS. But in many materials, RS is small, at least smaller than 30. And in that case, we can still seek interaction effects or new phenomena that, as I said, that we do not expect from the constituents by two methods. We can either apply a large magnetic field, and this has been the workhorse for physicists dealing with, let's say, or looking for correlation effects. And the other one is to use a periodic potential to generate flatter bands, to realize systems in which electrons behave as if they are heavier than they normally are in free space. Okay? And this actually is exemplified by two platforms. So the first one is a lattice. So any solid, any crystalline solid, has actually a periodic potential, right? So basically atoms are arranged in a certain structure, and the point is that the highest the electrons in the S or P shells are relatively free to move, and these, if you are relying on the behavior of these high energy electrons, we're going to have metals or semiconductors. But as we go down in the periodic table, we also have atoms with unfilled D or F shells. And these electrons, as you might remember from chemistry, they're much more closer to the parent atom, and therefore they cannot move as easily because of the Coulomb attraction to the nucleus. Okay, so that means that their ability to move, so their response to external forces, is much more weaker than what you would expect. For example, the response of a free electron. So the effective masses in these systems can actually be very large. It can be 100 times larger than the free electron mass. And this is the phase diagram of a cuprate material. I'm not sure which one it is now, but it basically shows the phases that the community has measured as a function of temperature and as a function of the hole doping in the system. So basically you have many materials. Each one has a different dopant atom that changes the structure. Okay, so if you have no dopants, it's an insulator that is antiferromagnet. So all the spins are arranged in opposite, the neighboring spins are arranged in opposite directions. And the interesting things happen as you start doping. Then you get this D-wave superconducting dome, which can have a critical temperature that is on the order of 100 Kelvin. And this actually, when discovered in '86, created an enormous interest because of the fact that it looked that there was a jump in critical temperature by almost an order of magnitude, and there was the hope that this can be pushed all the way up to room temperature. This still hasn't happened, but understanding why there is this relatively high temperature superconducting phase upon hole doping is still an open problem. And understanding it is believed or hoped that would lead to designing materials that can actually exhibit room temperature superconductivity. Now, to understand what is going on here, the physics community went to the other extreme, which is to put atoms in optical lattices. So instead of a periodic potential generated by the ionized atoms, here you have a periodic potential generated by interfering laser fields. And instead of electrons, you have atoms that are sitting in or subject to this periodic potential. The energy scales, length scales cannot be more different, but the whole research in cold atoms is driven by the idea that by this very tunable system, you can actually understand what is going on in the actual material systems. Okay, so you can think of this as a very tunable computer that we can actually use to calculate, an analog computer to calculate what is happening here. Okay, it has no functionality other than, or as much of a functionality as a computer, but it has full tunability. So what has what I'm going to tell you about is a new platform that lies somewhere in between these two extremes, which has in between energy and length scales, and that allows for a controllable solid-state platform that allows for correlated electrons. And I'm going to tell you more about this. Okay, so I think I gave a talk here 5-6 years ago. I already told you about the 2D material. So this is the new game in town, which started with the discovery of graphene about 20 years ago. And basically, it was realized since then that there are about 5,000 materials in nature which can be described as 2D materials. What is meant by that is this, that in these 5,000 materials, you have atoms arranged in a way that within a layer, they are subject to very strong covalent or ionic bonds. So these bonds are very strong. They're very difficult to break, but different layers, as they're stacked, as found in nature, are coupled or bound to each other by weak van der Waals bonds. So what that means is that it is very easy to peel off layers and go down to essentially a sort of material that is a single atom thick. Okay, so this could be a graphene, which is a semi-metal. So upon exfoliation with low-tech tools like Scotch tapes, you can create structures that can be 100 microns in size, and that are basically literally single atom thick sitting on a substrate. And there are all kinds of other materials. There are insulators, boron nitride, semiconductors, the transition metal, the chalcogenides, which I'm going to talk about. And then you can also stack them up to make a new van der Waals heterostructure with new functional properties. Okay, so this was the excitement in the system, in the community, I should say, up until 2018, when it was realized that there is another degree of freedom that comes in this stacking process. That is, instead of trying to align these layers nicely and carefully, what you can do is that you misalign them while stacking. Okay? So in this case, this is a simulation of two molybdenum diselenide layers. These are semiconductor monolayers. And if you introduce a finite angle, when you stack these two together, you see that there is a new superlattice emerging in the system. And this superlattice means that electrons now in this bilayer material, twisted bilayer material, are going to be subject to a periodic potential on a longer length scale. Okay? And there are some special sites, high symmetry sites, where let's say the chalcogen atom sits on metal, or metal atom sits on chalcogen, or metal atoms sitting on metal atoms, and these actually create the potential variation within this unit cell. So the unit cell will be as you see here. All right, so this was proposed back in 2011 by Alan MacDonald and was spectacularly demonstrated by Pablo Jarillo Herrero's group by using graphene. So this is really remarkable in the sense that graphene actually, electrons behave as relativistic particles. They are massless. And what is remarkable, to me at least, is that when you stack two graphene layers with the finite twist angle, and in this case it has to be precisely 1.1 degree, then you find that even though you started out with massless electrons, you generate a very flat band, meaning that the effective mass of the electrons that you dope into this band is extremely high. And that means that the system will be subject to correlation effects. And what they did then is to take this material, one material, and instead of trying to externally dope it, they applied a voltage, and this voltage allowed them to change the charge density and take the system from, let's say, in this case, a metallic state to a superconducting state, then to an insulating state, and to superconducting state, and so on. So in this way, the phase diagram that they obtained looked a lot like what the high-TC superconductors exhibit, with many different sort of phenomena or properties existing within the same device and purely electrically tunable. So you can think of this as an extension of semiconductor, which allows you to tune between an insulator and a reasonable conductor. Here you can actually go from a correlated insulator, interaction-induced insulation, to a superconductor or to a metallic state. So this essentially started an ongoing research in this field, where it was realized that this is not just of interest for making sort of new devices, but also for exploring new physics. And the same physics applies in when you use semiconductor bilayers. And so in this case, this is a calculation for a particular structure, tungsten diselenite, moly diselenite. And what you see here is, let's say, the top valence band, and the width of this band is telling you about how large the kinetic energy cost of this material system is, and that can be much smaller than the characteristic interaction energy. And I should say that in this material system, you have two kinds of, normally we talk about electrons having spin up or spin down, could of course be any superposition. Here, the spin is tied to this a degree of freedom, so-called valley. Okay, so what valley tells us is that these electrons actually have a chiral motion. If they're spin up, that means that they also have an orbital angular momentum of, let's say, +1, and if they're spin down, then they have the opposite angular momentum. So whenever we say spin, that really means that the spin is tagged to this orbital angular momentum, the freedom. Just mention that in case it's I'm going to use it. So what makes then twisted 2D semiconductor research interesting? So basically, there is a substantial effort on basically exploring the frontiers of superconductivity, and that means that the community is searching for new mechanisms that can enhance the effective attraction between electrons, not just using the phonon-mediated interaction, but using excitons or magnons, and in this way try to maximize the attraction and therefore the critical temperature, the temperature at which you see superconductivity. And this comes to the second point. The community is trying to understand what the limits to superconductivity are. Okay, so in that case, what we mean is not necessarily going to the highest critical temperature, but understanding how high the critical temperature could be in comparison to the Fermi energy, this characteristic kinetic energy scale. And then the other search direction, which I'm going to tell you about, is topological states of matter, where you have new emergent states of matter, for example, exhibiting quasi-particles that have fractional charge and statistics that is neither fermionic nor bosonic. And the goal is how to manipulate these quasi-particles, with the one application being fault-tolerant quantum computation. All right, so with that introduction, I'm going to sort of tell you very briefly about how we can use excitons as a spectroscopic tool to understand correlated electron systems. And then I'll tell you about recent experiments where we use optical control or optical pumping to control topology of two-dimensional materials. And I'll tell you what I mean by topological states before that. But first, our spectroscopic tool is excitons. And the idea here is rather simple. So this is the same semiconductor band structure, generic. So we have a filled valence band and empty conduction band in this case. So a photon comes in, it can excite one of these electrons into the conduction band, but because the electrons are all around, the excited electron sticks to the hole that it has left behind in the valence band. Okay, so this is the state that is called an exciton. So it's a hydrogen-like state, just like an electron likes to stick, even as we excite it, it likes to stick around the proton in hydrogen. Here, the electron that we excite likes to stick around the hole it has left behind, because that hole, that state that doesn't have an electron, has an effective positive charge, right? Because it has one less electronic charge than all the other states. So that's how one can think about it. And then this exciton electron-hole pair can recombine and emit a photon, and then that photon tells us about the nature of these bound states. Okay, so that's our spectroscopic tool. What we want to do is we want to excite the system with photons and generate these excitons, but we will be looking at how the properties of these excitons are modified due to the presence of electrons or holes that can be in non-trivial states, right? Topological states, superconductivity, etc. The question is whether we can read out what the properties are. And this will be particularly easy when it comes to reading out the magnetization or magnetic properties of the electrons. This is what I want to show you. So here is a gate scan of a monolayer in this case. So basically, when there are no carriers, we have an excitonic resonance. So if I take a line cut, so this is a heat map, so there is a resonance that is nice and narrow, but not terribly interesting. Now, when you inject the electrons, then the spectrum changes. So the exciton interacts with the electrons and tells us some information about the electronic system, like how its effective mass is, whether it is incompressible, etc., etc. Right? So in this case, we will be mainly interested in this lower energy new branch, which we have identified or called an attractive polymer resonance. So I'll use the acronym AP. So it's only there when we dope the system. What's more is that it's only sensitive to a given polarization of the incident light. So if the electrons are occupying in this spin down state, this spin valley state, then I can see this resonance strongly in sigma plus polarization, whereas and I see very little in the sigma minus polarization, because in this case with the magnetic field, I made sure that most of the electrons occupy this valley. So the strength of these transitions, or their ratio, directly tells us, and this we can show mathematically, is the degree of spin polarization of the system. So if all the electrons are spin valley polarized, then this resonance is not there, and the relative ratios, as you can determine from these line cuts, tells you the degree of spin polarization in the system, and this is what we are going to use. Okay, so now the experiments. So the experiments are done in a bilayer molybdenum ditelleride. So this is again a semiconductor system, which due to the details of the actual band structure, has rather special properties, that it has deep moire potential and also sizable tunnel coupling. Okay, and this results in Chern bands or topological states of matter. So I will not try to explain these in detail. I want to tell you some generic or general comments about what topological states of matter are. And roughly speaking, these are materials or states of a given material where the properties can be described by a global invariant. That is, this invariant is not a property of an individual electron, but all the electrons that you have in the system. Okay, so generic analogy that one uses or forms is between ball and donut. So you can have two, let's say, a silicon, right? The same material, you can shape it into a donut or you can shape it into a ball. And you will argue that there is a fundamental difference between these two materials that you cannot see by using a microscope and looking at individual atoms. They will look the same, but their overall shape is different, and you cannot transform one to the other without breaking or melting it, right? So in this case, in the case of topological states of matter, the shape of the electronic band is more difficult to visualize. It first of all, one needs to look at the nature with which the bands are connected to each other. But what is important is that this shape is described by an integer, that it could be 0, 1, -1, 2, -2, etc. Okay? So it's a property that can be quantified by an integer, and it's a global property of the electrons. That's what is special about a topological states of matter. Now, these properties, this integer is resilient against local perturbations or defects. And you can see that, right? Because this integer is called a Chern number. It cannot be 0.9. It can be either 1 or 0 or -1. So, and this change cannot be done by small perturbations at small parts of your overall system. So the system is resilient against these perturbations, and that's gives us a hope that it can actually be useful for some devices. And so the other thing is that in most topological materials or topological insulators, the material itself is insulating, but it has surface or edge modes that are perfect metals and chiral metals. So electrons always flow without dissipation in the same direction. So rather unusual properties. And maybe what is most important for what I'm going to tell you about is that in 2 dimensions, the topology is directly connected to ferromagnetism. So whenever you have a topological state of mind, at least in 2D materials, we see that they also exhibit ferromagnetism. And this is the property that we're going to use. Okay? And the question that we addressed in our work, so I'm finally coming to that, is whether we can control ferromagnetism and, along with it, the topological state by using optical control. Okay, so as I said, I cannot do this by acting on locally, but with photons, with light, I can act on the whole material, and then I should be able to convert the topological number integer from 1 to -1, or in the cases that are of more interest, a fractional number to another. All right, so signatures of topological states of matter. These were discovered 45 years ago. What you find is that when you make a transport measurement, which I will not do, but I want to discuss it. So what you do is you run a current through a slab of material, and then you look at the voltage drop, the so-called longitudinal voltage drop between source and drain, and also the hole voltage, the cross voltage generated in leads across. And what you find is that whenever you reach a quantum a topological state, like the nu equals 1 state, this is from quantum Hall effect, then this resistance, the longitudinal resistance, is 0, a bit like in a superconductor, but there is a difference because conductance is also 0. And then the whole resistance is quantized, in this case, in units of E square over H. Okay? And what is really remarkable is that this quantization is amazingly accurate. It's always independent of the material that you have, provided that it's good enough. It's accurate to 1 part in 10 to the minus 9. Okay, so it's now used to basically to quantify or categorize resistance, the value of resistance. And then what you see is that there are also fractional values in which, again, the same physics happens. For example, in this 2/3, you again have a plateau, and then the longitudinal resistance is 0. Okay? And this now is a so-called topologically ordered state. I will not go too much into that. What I want to show is that whether a state is topological or not, you can understand by measuring where you find this, let's say, whole conductance as a function of magnetic field and how it depends on the filling factor. So if this property is vertical, that means it's non-topological. If it has a finite slope, that slope is proportional to this integer that also defines this quantized conductance value. All right, so we want to do optical spectroscopy. So again, we take this system, we apply our light. When there are no holes in the system, then it's boring. It's just like any other semiconductor. But when we inject holes, in this case, this really works by injecting holes into the valence band. Then what you find is that time reversal symmetry is spontaneously broken. We get a magnet, right? So all the holes occupy one valley and one band with the definite Chern number. Okay, and this has optical signatures. So first of all, how do we know that optically? I told you how to detect it in transport. How do we know optically that you have a topological state? You look for cusps in this case photoluminescence, and then look at how with magnetic field this cusp moves. Okay, so the slope again tells you about the topological Chern number through the strata formula. This was pioneered by my collaborator Shadong Xu about 2 years ago. So this I will skip. And he also did transport and so that what I showed you with quantum Hall systems appears also here, that you have plateaus of Hall conductance and zeros in longitudinal resistance in the absence of a magnetic field. Okay, so this was then the experiment that demonstrated that this is a topological state of matter. And what is also interesting, and this you do not see here, is that actually in between this 2/3 and unity filling, there is a superconducting phase that seems to require high-quality materials. And this is a topological superconductor that was seen by a group in China. Okay, so now let me come back to our experiment. So we look at the reflection from the device, and we do it in a polarization selective way. So this is sigma plus, this is sigma minus. We basically go to zero field, and we see that these attractive polaron resonances that I told you about, we only see it in one polarization, none in the other. So just like I described to you, this tells us that all the holes in the system are spin polarized. Okay? And this we can then check by essentially tuning the magnetic field and see that as we tune, let's say, the magnetic field down, we can switch the degree of polarization rather abruptly, and there is a nice hysteresis curve which is generic for first order phase transitions or for Ising, so-called Ising ferromagnets. Okay, so even at 0 Tesla, you have a finite magnetization, and that magnetization depends on where you are coming from, whether you come from a higher magnetic field or positive magnetic field or negative magnetic field. And this we check at low powers optically, and we see the same hysteresis curve for any polarization that you can choose. Okay, so in this case, this was done at 2/3, so the Chern number also changes from 2/3 to minus 2/3 to 2/3, etc., with magnetic field. That by itself was known before. But what we did then is to see if we can control this optically, and so we devised this pump and probe scheme where timescales are seconds. So we pump with sigma plus, probe for several seconds, etc., etc. And what we see then is that as we increase the power from 2 nanowatts to 100 nanowatts, these are still low powers, then we can actually kill this hysteresis curve and basically enforce that at zero magnetic field, the degree of magnetization is determined by the degree of circular polarization that we apply. We can apply sigma plus and push the Chern number to minus 2/3, and sigma minus, and we can push it to plus 2/3. Okay, so this is how it looks. Then, as we increase the power, we can initialize in a state with Chern number 2/3, and then the system will switch with sigma plus and will remain the same with sigma minus. And then, if we apply linearly polarized light, we destroy the topological property. So that's also an option. All right. So don't know if I will bother you with this. We see that actually even though the system is ferromagnetic all around in this Chern band, it's easy to flip its degree of polarization or Chern number when it forms an incompressible state. And since I did not describe what these are, I will skip that. And I want to point out that even though I told you what we can do with sigma plus excitation, if we use sigma minus light with another resonance, another frequency, we can also do the same switch. So this is not an angular momentum transfer, but we're basically using polarization or spin selective excitations to push the system in the direction that we want to go. All right, so as a potential next step or application, what we can do is we can actually use shape beams. In this case, this was a simple Gaussian beam. So we prepare the holes in one Chern state, +1. When we apply our laser pulse, we can flip the Chern number in the region, or the topological property, this topological integer, to -1 in the region that we excite. In this sort of region here, that's due to defects in the system. We probably have different puddles with different Chern numbers. That's why it looks like it's a continuous change. In an ideal system, this will be flipped between one and the other. And if we can get such high quality materials, we can define topological circuits all optically. All right, so basically I want to end by saying that, the key concepts in condensed matter physics these days involve, or let's say there are three pillars: strong correlations, interactions, which is what I emphasized initially, topology of the bands, and frustration is another sort of source of interesting physics and interesting properties. And then non-equilibrium dynamics, that is what happens if we drive the system optically, can we change its physical properties? And there are these are fields of activity that basically connect these pillars. And I would argue that what we've done is in some way connect all these three, because we used a non-equilibrium driven dissipative system in a strongly correlated system where with non-trivial topological properties. All right, I'll stop here. Thank you.